paper 2, I'm going to see if I can run through just population sampling really quick for you. So this is going to cover mark and recapture, belt transects, random sampling, and align transect. So if we're looking for the population of sharks, because they move, we can mark them with satellite tags, and they're really big, they're migratory. If it was a kelp forest, there wouldn't be any point giving them a mark or a tag. Instead, we can do a line transect and estimate the amount that touches the transect, or we could use actually near infrared imaging to estimate their population size. If it was mussel beds, something to consider is they don't move, they're small, there is a lot of them. Putting a tag on them would be pointless because they're not moving at all. For that, we would use a framed quadrat or a quadrat, and we could do random sampling. We could also do a belt transect with a line. And the line really just keeps you honest and make sure that you're sampling in that area. It can also just be used to record if a species or an organism exists there. For humans, we do a census. So these videos are some that I found awesome videos. They are for A-level biology, and so some of the content is more than what you would need in marine, but she covers what you would need in just in marine science.
Hi everyone, and welcome to Learn.
Okay, mark, release, recapture. So we could use a camera to take pictures of dorsal fins. We could use a satellite tag for large mobile species like turtles and sharks, or non-toxic waterproof paint. This will calculate the abundance for mobile species when there's way too many to count. Sharks, turtles could use a satellite tag. Snails, you could use some non-toxic paint. Dolphins and whales, you could do dorsal photography because their dorsal fins are kind of like our fingerprint. They're very unique to them. How you would carry this out. So safely capture some organisms. You can mark them with non-toxic waterproof paint. You would count them. This would be your N1 value. I just realized M2 is moved over. That's frustrating. Sometime later, or whatever the appropriate timeline is, a second sample of organisms should be taken at the same location during the same time of the day to try to keep everything standardized by the same people using the same method. This time in your sample, you're going to look at the marked and the unmarked population, count them. This is your N2. The organisms that did have the original mark from the first capture is your M2, and you're going to apply the Lincoln index to look for the abundance of species. Limits. This one has the most amount of limits. They might be returned to their habitat in a clumped distribution where you didn't necessarily gather them in a clumped distribution, but when you would return them, you might inadvertently just dump them all, hopefully not dump, but put them back in the same place altogether. And that's going to make all of the marked individuals kind of congregate together just the way that you put them back. So disperse them the way that you found them. The mark could harm the organism. It could hinder camouflage ability, which would increase predation. The mark could come off. If it's photos of dorsal fins, you could just really have a bad picture. Or those organisms could get scars or damage later on, and then when you photograph that dorsal fin, you think it's a new individual when it's really just the same one with more damage. The Lincoln index does not account for births or deaths. Immigration or emigration, we're going to assume the population is unchanged, and that's just like an assumption that gets made with it. If it's a satellite tag, depending on the type of satellite tag, those organisms need to be at the surface for a certain amount of time. Could be 15 seconds, could be 60 seconds, depending on the quality of the tag. And then it can ping to like an acoustic sensor to go to a satellite. So some organisms that would use a satellite tag, they are migratory, they can go very far. Okay, a little practice. Some examples. Limits. Well, not even limits, but sorry, things that you would need to keep standardized. Here's some limits. I think that's from specimen paper 2. Random sampling. And then I won't play this video, but Quadrats with Kate is a quick one. It's great. It is not me. We could use a framed quadrat or a drone, take an aerial image, and then once you have that aerial image, you can upload it to a computer and place like a grid over it, and then just number those grids, and then a random number generator, literally like random number generator, Google search. Google has it embedded into their website, and you choose a selection of numbers that you want randomized. A camera to take photos of your quadrat results, perhaps. So maybe you can't just, you're underwater and you can't take a picture of everything, or the temperature is really cold and you want to get out of there, you can take photos. So this is look at species abundance, their amount. When a habitat's too large or there's too many to count, you can also look at richness, but you might be isolating one organism at a time. These organisms don't move, and typically it's a uniformly distributed throughout the environment. So it's not like a drastically changing environment, like a rocky shore. This would be pretty uniform.
A quadrat.
Okay, and I'm going to start my first period. Okay, I'm back. Just did a couple hours of classes. What purpose would you use random sampling? It's for finding species abundance when there's too many to count, but you're also identifying species there, so that could be richness too. This is for organisms that aren't going to move, because you can't count things in a quadrat or estimate their percent if they're moving. So corals, kelps, seaweed, mussels, typically things that are uniformly distributed. So the habitat isn't going to be changing a lot, like on a rocky shore. The habitat's going to change a lot, especially at different tidal zones. Seagrass meadow, same thing, or maybe just a specific zone of the rocky shore. How they carry out this method. So you would toss the quadrat in a random location, but that is limited by how far you can throw it. And if there is a little bit of a slope, then that quadrat can like tumble. So we can use computer models to randomly select areas and then eliminate bias. Okay, I was going to see if I could move my screen, but I don't think I can. So you could literally just upload an aerial view, like a drone photo, or just a photo of that habitat. And I did this in class. I did that with a rocky shore. And then on like Google Slides, I just inserted like a grid to section areas off, numbered each box. And then you could just go like randomnumbergenerator.com or Google random number generator, and a random number could be selected for you. Those will be like, that would be the areas that you would sample, and that eliminates bias. Because otherwise we might pick areas that are like very abundant, or if we're short on time, we might pick some that are not abundant, but that'll be with the limits. We're going to count the organisms in the quadrat. Repeat at least 10 times, and you want to do maybe some different locations, not just that one short location. To calculate the mean of your data, you're going to add up the sums of all your quadrat, and then you divide by the amount of quadrats you took. Fine, and then that'll give you the amount per area, and it really depends if the area is determined by the size of your quadrat. So if the quadrat is a meter by a meter, it's a meter squared. Half a meter by half meter, it's half meter squared. If you want to find the total population now, like so you just took little samples of the population, you would look at how big the full area is, and if you know how much you have in a small section, you're going to apply that number to the full section. Limits. Visual biases could cause quadrats to not be tossed in random locations. Our eyes typically are drawn to high populated areas. There's not enough samples to account for the entire location, so it might be a little bit sparse right on the edges. We need to account for that. The areas might not be selected at random, so we use a random number generator. Okay, there you go. The quadrats that have the lines in between is called a framed quadrat, and those help actually if you're going to estimate percent abundance, like what portion is this actually covering. All right. Line transect. So a line transect, use a rope or a tape measure. Could also use a camera to document results, depending on like the conditions, if you can't stay out in a field long. This is to record like a species existence. So are you there? Not how many, just do you exist? And we would call that like the species richness or the richness of an area. So how many different species there are. It's not abundance because you're not counting the total amount. It's just what exists on the line. It also helps to identify like the area and the habitat they're located. So the picture you have here, they're actually on the lower zone, the lower tidal zone of a rocky shore. This would be good to use on a rocky shore because your species are zoned based on the abiotic and biotic, but more abiotic factors they can tolerate. All right, the habitats are not uniform. That's when you would want to use this. Habitats change with distance, so the further away from the shore. So rocky shore, that's intertidal, sandy shore intertidal. Roper tape measure, maybe 30, 50 meters long, depending on how long your area is. And having regular marked intervals. Below, I'll tell you why. You're going to record the species presence and their distribution. So do you exist? And by distribution, like where within that habitat do you exist? Are you in the lower zone? Are you in the middle zone? Are you in the high zone? Are you in the splash zone? Does not record abundance. So it's literally just if the species is touching, if it's touching the line, that's it. That's it. If it's systematic, you're doing this within a regimented system. So you're looking at species presence and where they're at, where they're distributed in regular intervals. That is like the statement you want to say. It's in regular intervals. So every half meter, every 5 meters, every 1 meter, it's up to you. If it's continuous, you're just continually looking for species touching the line along the entire line. Limits to this method. Only species presence is recorded, not their abundance. Just do you exist? I don't care how many's in your party, just are you here? That's it. It doesn't account for the entire habitat because it's wherever the line is. The line placement could have a visual bias. So the areas could specifically be chosen where there's a lot of species. Or if there's a time constraint, or maybe it's cold outside, or the weather's bad, or you are tired, literally, those are legitimate things that happen, then you might just choose an area that you know is not going to have a lot of species and then end it quick. There we go. So you can't tell a percentage. You can't use a quadrat or you're not counting. It's just, does it touch? All right, and the last one we need to talk about is the belt. Practice exam question. So just using systematic or continuous sampling. Systematic is going to be regular intervals, recording species, and then the continuous is along the entire length of the line. Belt transects are called belts because it looks like where the quadrat is, that is the buckle, and then the line is the actual belt. All right, so tools you can use. Framed quadrat, you could use an AC4 scale. I have it at the bottom. This is when looking at the quadrat and you're going to estimate giving it like a letter. A would mean it's abundant. B would say it's, C is that it's common. F, this organism is frequent. O is occasional, and R, it's rare. And the percent it's associated with is the percent coverage inside of the quadrat. Again, you can use the camera to photograph results and see it later or to look back at them. And a line transect, so literally the line, like you see here, line, and marked off at regular intervals, which is why like a tape measure is also helpful because it's already marked off specific intervals. So it's similar to a line transect. It's going to record species presence, but you can also use the quadrat to give data on abundance. So how much is there? Organism distribution and abundance is on like a rocky shore intertidal zone or a coral area, sandy shores. That would be when you could use this. You're looking for where are they located in the species specifically. What species are you? Where are you located? And what is your abundance? Could also use this well when the habitat is changing a lot with distance. So the further away from the shore it gets, or the as depth increases. This is an area that's not uniform. Uniform would be more like a muddy shore. The seagrass meadows. How you carry this out? It's very similar to the line transect. We're just adding in now the quadrat. We use the quadrat random sampling. Systematic sampling, a framed quadrat, is placed at regular intervals beside the line transect. And again, whatever you want to sample, is it every meter? Is it every half meter? Continuous, you use the framed quadrat next to the line. So in this YouTube video, it is next to it. That's fine, as long as you maintain that the whole way through. Or, like you have in this middle picture, the line is going through the quadrat. That's fine as well, but you're going to just, whatever the method is, you maintain it. You could have the line and then do the quadrat like half a meter away from it. It does not matter. It doesn't matter. As long as you keep that same measuring amount the whole way through. And then to calculate species abundance, we're looking at the percent covered inside the quadrat, and you can use the AICE scale. Or you could literally just say, this is like 60% covered. But they could use AICE scale. Limits. This does not account for the entire habitat, once again, because you're only sampling what's along the line. The line placement could have a visual bias, similar. Person could choose a dense area to lay it down. They could also be like, I want to get out of here. I'm going to choose an area that's, I know there's not going to be a lot of organisms to count. Easy day. So there could be bias. And then if you are assuming percentage, there's not an exact situation for that, especially if it's to make it easier so you don't have to count. That could be different with who's ever assuming the percent abundance. All right. Example exam questions. I'm actually going to kind of just click through these a bit. Systematic survey. All right, so different sampling methods of a belt transect on a sandy shore. So the line essentially, and then your different, this is systematic, and this is continuous the whole way down. There's your line, there's your belt. Here's the quadrat, making it a belt. Again, they're taking pictures later. We can include safety and ethics in this. You can include ethics whenever there is not any organisms used, like if you were doing density and salinity, or boiling point, freezing point, and salinity, because there's no organisms being used. For that, you should just say there is no ethical considerations or ethical protocols due to no organisms being used. Literally, quote. And you can get a mark. But you would just need to at least say, like, oh, I considered ethics, and there's nothing here that would be ethically unsound. So safety for sampling. Wear non-slip shoes. Be aware of tidal changes. Wear sunscreen or sun-protected clothing. Wear weather-appropriate clothes. Sorry. Stay hydrated while in the hot sun. Look for massive weather changes. Ethics. Stay away from breeding grounds or offspring nests. Yeah, okay. So like nesting areas. Do not sample areas that are protected without approval. So if it's like an MPA, like a marine protected area, do not remove species from their habitat. If you're doing mark recapture, return species to the area that you found them, because you're going to take them to put a mark on them. Use non-toxic paints. Let's see if I can get this actual page. Okay. So the Khalid bin Sultan Living Oceans Foundation. This is a great video. I can't play it due to copyright restrictions, but this is a great video that does cover every sampling technique. And I don't think it's too long. 8.5 minutes. All right, this is, can I zoom in? Can I zoom in? So I made this quickly for my students yesterday, just so we can not see these things as being separate. Okay, I don't want that. Sorry, not seeing these things as being separate, but that there's reasons for why like they're going to exist together. It's not that Spearman's, Lincoln's, and Simpson's is a completely separate topic from these sampling methods. So what we just covered were different sampling methods. We've marked recapture, and what I put in here for how we do it, that was exactly what's on the slide. Methods for line transect, methods for random sampling with the quadrat, and then the belt transect. And does it tell you like the species or the amount? So that's the richness or the abundance, and then their limits. It's literally the same thing I have in the slides, but they exist together. So it just depends on what kind of data you want. So here's how we capture population sizes for organisms, right? There's 4 different ways. And then what do you want to do with the data? So if you want the population of just one species, if it's something that can move, we can do a Lincoln index, which is mark recapture. There is not a data range constriction. You use this could be any amount, like any population is fine. That just tells the species abundance. It's not richness because we're not looking at the different types of species. We're just looking at one species. Well, then if you were like, well, I have this data and I want to see like, is there a relationship or a correlation between the abundance or like, yeah, amount of different species that have a shell and then the distance from the low tide zone in a rocky shore. So how far away they are, and then the different species that have a shell. If you wanted to see if those 2 things actually correlate together, you would do a Spearman's rank correlation. So this is to identify if there's a correlation or a relationship or like a pattern between 2 sets of data that are not normally distributed. And what that looks like is it's not in any sort of linear fashion. So you're not going to have like, as the amount of shelled organisms start to increase, then I see that they're further away from the shore. There's not data like that because with the quadrat and random sampling, you're going to sample random areas. And so maybe that data does not follow any pattern numerically. It's not in a numerical order. It looks like it's going to be scattered. You would do a scatter plot to see if there even is a correlation. If there is, then we can run like the Spearman's rank correlation test, which you don't have to know the formula for. You just need to know like when you would do it and how to apply it. The data range can be -1 to 1. -1 meaning that it's a negative correlation. So if the steepness of a slope at a sandy shore is increasing, the biodiversity starts to go down. And that line does look like it's a negative correlation. Or it could be +1. +1 is a perfect positive correlation. So if something is increasing, another thing is increasing at the same time. In nature, perfect positives, perfect negatives really don't exist. But you could identify if your value is going to be close to a -1 or close to a 1. That would be giving it a strong correlation. Just, is it negative or is it positive? It's tedious to remember the data range. So something that you can, I tell my students, Spearman's, we're Spearman. Like you have a man, so that's your +1. And then if you spear a man, -1. You don't have that man anymore. She speared him. I always say, I don't care how you learn, I just care that you learn. So we can move on from that. Simpsons. So another teacher had said this to me at a Cambridge training, but Lincoln was one man, one person, Abraham Lincoln, one person. You use Lincoln index to find the population of one species. Simpson's index of biodiversity, you take into account all the species, just like the Simpsons TV show, like the family, there's a lot of different people there. You look at the whole family, the whole group. So Simpson's index of biodiversity, we're not just looking at one species. We're looking at all the species and then their abundance. And that range is different. That goes from a 0 to a 1. In the name Simpsons, the I, we could replace that with a 1, and then the O could be replaced with the 0, and that's the range there. If the value is closer to a 0, that means it's not very biodiverse. It's probably like a hydrothermal vent or a sandy shore. The species diversity is low. Their genetic diversity would be low. They need a lot of adaptations to live there. Feeding relationships are low. Niches are low. If there is a disturbance in the environment, there's probably not going to be a lot of adapting to it, and it's going to cause a big disturbance. Like there will be a big ripple effect from that. Likewise, though, closer to 1, coral reef, rocky shore, especially in a tide pool, probably like a mangrove, those places are more stable. They are more biodiverse. They're going to have a lot of different species, a lot of different feeding relationships, a lot of producers, a lot of niches. If there is a disturbance or there is some sort of ecological upset, then they will be able to kind of bounce back from that, and they're going to be able to adapt to it, and there really won't be a massive change in that ecosystem. So just to recap, you have different ways to measure the populations of species or just of one. Those are your sampling methods. And then what do you want to do with that data? Do you want just the population of one species? Do you want to see if the species is increasing or decreasing, or population is increasing or decreasing because of this other factor? Then we'll run the Spearman's ring correlation. But correlation does not mean causation. It does not mean that they're the cause of each other. Just because they seem to follow a pattern, it does not mean that they are the cause of the pattern. It could just be a coincidence. Simpson's index is to measure if an area is biodiverse or not. But ways we can calculate those, the data we can get for those, is through the methods of sampling. Maybe this helped just a little bit. Good luck today.